Hello. Good afternoon, fancy meat computers. People are complaining about the labs. Uh-oh. Are the labs hard? The first lab is supposed to be easy. I don't know. Oh, maybe it's different labs from my labs that you're complaining about. Confusing with unclear instructions. Yeah. In a, yeah, online labs are the worst, generally speaking. Yeah, in a parallel universe, I would be redoing the course materials this semester, but I can't, so, you know. Yeah. I'm scared to blow my house up or electrocute myself. Yeah. The documentation for the labs is difficult to understand, not due to the course, but due to how in-depth the datasheet and programming guide is for the STM. Yes. Well, that generally means that what you need is a quick start guide. Right. Alright. Well, you know. I'm just going to close the door. life powers activate. Well, should probably get moving on the lecture today. Is that out of frame? Mostly. Okay. Cool. So, one important announcement before we get started. I've decided to move the quiz to Wednesdays. I mentioned I was going to do this last week, and it took me until Monday, today, to actually get the announcement out about it. But, yeah. There we go. So, we're going to have the quiz during our Wednesday lecture time. I have set the quiz to a 10-minute writing duration. I have set the quiz to start 5 minutes into the lecture, so we'll have our, like, intro period, and then we'll, do the rest of it. When during the class is the quiz? 5 minutes in, my friend. 5 minutes in. 5 minutes. So, there you go. Good. So yeah, that's all I really have to say about that. It is, the reason for that decision is that basically, it's better if everybody does them all at once. Is there a quiz in this current week? There is a quiz in this current week. There will be a quiz on Wednesday. My God. I'm gonna have to shut the... Ugh. Silence, fool! Don't you know I'm teaching? How long? Yeah, the quiz, yep. You please don't worry about the quiz. It's not that bad. It's a quiz. It's like 6 questions, 10 minutes. Mostly like true, false, fill in the blank and matching type stuff and multiple choice. That's the kind of thing you're looking at. So I hope not to rupture any stomach linings with it. Will there be a lecture live stream going on during the quiz? Yes. Is that a Motorola ringtone? Next question, please. I'd like to plead the fifth. Yes, I have the cheapest phone in existence. Like, actually the cheapest phone in existence. Listen. Aren't you glad I'm not planning on doing a 24-hour final? Yes, it will be done through Avenue Quizzes. Yeah. Anyway. So, let's carry on, shall we, with the with our lecture material. So, we're last time we covered some general architectural details, and hopefully we hammered out some interesting components of the sort of memory instruction interface. Yeah. Oh my god. What have you done? Now everybody's just going to talk about the final for, like... Oh my god. Okay, for those of you who were, like, into MP3 last semester, I really, really liked the Collatz question. I think it was pretty at the end. Like, I don't know if some of you tried, like, running that algorithm for, like, very large numbers of numbers, but, like, if you ran it for, like, you know, say 5,000, you got some very interesting and organic-looking structures. But, yeah, anyway. But, yeah, anyway. I will not apologize for setting an exam. So, anyway. We're going to, Life was fun. Yeah, I like Life as well. We're going to talk about general purpose input-output. Yeah, maybe you guys will see the point of the bitwise question a bit more as we go on through even this particular set of lecture slides. The only thing I could do correctly was make me cry. Come on. Engineers don't cry over technical problems. Oh my gosh. So, GPIO. GPIO, of course, stands for General Purpose Input-Output. For those of you who are following along in the textbook, we'll be talking about Chapter 14, doing most of Chapter 14, except for a couple of bits. So, the question sort of becomes, okay, so it's fine and dandy to have this processor and be able to execute instructions. So far, we're not really doing anything different from what a normal computer would do, right? So far, we're just working with underpowered computer hardware, right? What really... will we go back to Chapter 2? No, we're gonna jump all around, so... there is no relationship between what week we're on and what chapter of the textbook we're on. Yeah. Oof. So... yeah. There's sort of an older style of doing this and a newer style of doing this. The older style was that you would have, like, special instructions, either in the CPU, and those would filter up to the level of C code as well. You'd have something like a special, what am I saying? Function. Yes. Wow, couldn't remember the word function. So you would get a set of special functions that we would use to configure the input-output pins of your boards, right? The new way of going about doing that is to have memory-mapped I/O. So essentially, this is, if you remember me talking about at the end of the last lecture, how you would memory map a peripheral such as an LCD, like a liquid crystal display, to your controller. You would have a region of memory addresses that are hooked up in hardware to whatever you want to interface with. So anything that you write into that address is sent out to the rest of the circuit. So that's kind of the idea with memory mapped input and output. Most CPUs these days do I/O via memory mapped I/O, It is a simpler and more convenient way to interface the devices. Each device is assigned to a memory address in the address space of the microprocessor. So if you notice from this guy at the bottom here, our SRAM, our instruction memory and our data memory are actually a small amount of our total memory address space, right? So with the memory mapped I/O, you're selecting one of these other regions and taking some of those addresses, and you're giving them, you know, you're having the circuit wait until something gets written there and then pushing it outward. The advantage of this, of course, is that the CPU can use its native load and store operations to interact with this memory, which means that you don't need special instructions to do that, which means you can reduce the instruction set size, which means you can reduce the size of the chip overall. Although you can reduce the size of the CPU, it does add more circuit to the back end of the memory, but yeah. Yeah. So, GPIO, the pins themselves, there's a reason we call them pins. Generally speaking, from the external human being's standpoint, what a GPIO pin looks like is actually one of these little gold-plated pins on the side of a board. The operation of these pins can be configured at runtime to perform quite a wide array of different functions, actually. I remember back in my day, when you had your little PIC microcontrollers or your little Atmels, certain pins were always dedicated digital input, certain pins were always dedicated digital output, certain pins were always dedicated analog input, analog output. Although I believe the things like pulse width modulation was something you could do with a general output pin. But these days things are a lot more configurable. You can configure the behavior of a lot of these things in software, which basically just means that there's more circuitry there, and you activate certain types of the circuitry based on the values that are being held in various memory address spaces. But yeah, good. Question. Is it one register per unique device or one register per device type? Well, that's interesting. First of all, memory cells are not necessarily registers, but it could be flash memory, for example. But it depends. We're actually getting there. The way that GPIO works, like, a GPIO pin is 1 bit, right? 1 bit of information. So what they do is they collect these things into what they call GPIO ports, right? So a port is a group of GPIO pins. So you would have, like, a number of GPIO pins corresponding to the number of bits in the data memory at the memory address that the port consists of, right? So, but let me just finish this slide first. So, the number of pins available to a processor is limited, obviously, because all things are limited, and normally fairly restricted. Like, anybody know how many GPIO pins the STM board has, just off the top of their head? The Raspberry Pi Pico uses programmable I/O, fancy GPIO, that is very cool. It allows you to direct connect to things like DVI and most digital signal standard directly. Huh. Yeah. Yeah, the definitely the trend recently has been to allow, yeah, like 50? Yeah, sounds about right. So, so these days, like when you get these larger ARM architectures, it's like more than one, yeah, for sure. Um, these ARM architectures are sufficiently large that they can afford these types of like optional extras. However, if you're doing a small enough pardon me, if you're doing a small enough application, right? If you're using a like, I'm not sure if the extreme low end of the ARM boards still beat like I'm not sure if they beat the like the little Atmels or not any at this point in time, but um if you're using like a super 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 tiny microcontroller, um it's possible that you'll be thrust back into a situation where the pins aren't nearly as configurable. So it's good to know that them being configurable is a recent development, right? So in general, there are 4 different categories of pin functions, right? You've got digital input, digital output, analog conversion, digital to analog or analog to digital, of course, and you have alternate complex functions such as pulse width modulation and LCD driving and stuff like that. There's 124 pins on the STM, but we don't know how many are GPIO. Well, yeah, sounds about right. So we're going to go through the first 2. Analog and digital conversion will be the subject of a later topic in this course, as will pulse width modulation, and I think you do LCD driving in one of the labs. So a GPIO port consists of a group of GPIO pins. All pins share the same data and control registers. So, in a memory mapped situation, you'd have one memory cell that maps every pin in the GPIO port. When a GPIO pin I is set as digital input, the binary data read from this pin is saved at bit I in the input data register. So, essentially how it works, right? You have this pin, right? You connect it up to the external circuit. The external circuit is either at a higher or low voltage. That voltage gets transferred and read by the pin, and the hardware takes whatever that voltage is and writes that into the register at the specific bit that is, if it's like pin 7, it'll be written at bit 7, right? Which is why you need to know how to use bitwise operations, because you need to know how to take a register and collect just the information coming out over pin 7, for example. And bitwise is how you do that. I mean, like, theoretically you can do it arithmetically, but to know how to do it in bitwise is far superior, because it's, like, very quick. Actually, I'll just show you how to do it. This is a lecture, after all. So if you had some, let's say you had you wanted the result, and you're trying to read pin 7. So it's, let's assume that's an 8-bit register, right? Bitwise and then dereference the GPIO port address, right? So this is commonly known as a bit masking operation. The result will either be this or it'll be 0. If it's this, then that particular bit is 1. Otherwise, that bit is not 1. If you want to get, fancy with it, you could also, move it down so that it's in the, the expected space. It's either 1 or 0. But, you don't have to get that fancy with it. So there you go. When a GPIO pin I is set as digital output, bit I in the output data register hold the output value of that pin. All GPIO pins in a port can be configured as input or output independently. So this is reading, bit 7. If we wanted to write bit 5 as high, we would do something like, GPIO port address is equal to this guy. And or, bitwise or, 5th. Yeah. There we go. So, regardless as to whether the bit 5 is high or low in this one, it will be high afterwards because, that's how OR works. And of course, if you want to toggle bit 3, for example, you use exclusive OR, like that. The other thing to keep in mind is that in C, you have available to you bitwise equals as a command. So you can literally just, save yourself some work there. But yeah, any questions about this so far? What did I mean by reading bit 7? So if pin 7, let's say pin 7 is connected to something like a push button, right? In order to use the state of the push button to control the program, you need to read the pin, right? Which means, like, the pin is all automatically being read. That is to say, it's being read and fed into the GPIO port address, right? But in order to get that pin, in order to get that information into the program at large, you have to be able to extract just that single pin from the entire port, and then you can use it. Wait, what? Yeah, bit 7 will correspond to pin 7, right? That's what memory mapped I/O means, right? Like, it's a mapping between the I/O pins and the memory. So the CPU only interacts with the memory. The hardware takes care of that messy bit in between the pin and the memory cells. So all you have to do is worry about it as if it were memory. What is GPIO port address? Like, where does it come from? How does it get its value? That'll be in the documentation. It'll be set by the this is like a constant that you have to look up in the documentation. using, yeah, if there is, yeah. If you use the included API, that's also fine, but, yeah. So we are extracting binary data. Yes, we are extracting binary data. Yeah, but, you know, it's also useful to know how things are working behind the scenes, right? It's like each controller will have 4 memory mapped I/O, for memory mapped GPIO ports. In the documentation somewhere, it'll state what the memory address is for that mapped memory. You then grab that memory address, dereference it, and then you can operate with it inside of your C environment. How does bar equals work? That's just, it's like plus equals, but with bitwise OR. Yeah. Do ports like USB work in a similar way to this? Yeah. Yeah, absolutely. The only thing about USB is that it's not just 4 pins, right? It's 4 pins with an included communication protocol. So, like, with USB, it stands for Universal Serial Bus, right? So it's serial communication. If I'm remembering correctly, the 4 pins in a USB are transmit, a receive, high and low, or like VCC and ground. But yeah, so yeah, like the USB, fundamentally it's performing these operations underneath the hood, right? So API stands for Application Programming Interface. It allows programs to communicate, essentially. Well, what it is it's allowing some programs to call other programs' functions, right? Back in my day, we used to just call them libraries, but people call them APIs now because that's more, you know, syllables. Yeah. So, people are not quite sure how this guy works. So let's let's take a real example of this, right? So let's say that we had a GPIO port. Like, once you dereference the address, you get something like that. That's too many. There we go. So you can see we're trying to set pin 5. Pin 5 is 0, right? So if we take logical OR bitwise OR, that is equal to the OR of each of the individual bits. So it'll be 1, 1, 0, 1, 0, 1, 0, 1, right? So you can see that this one, this actually works easier if you line them up. There, you'll be able to see. So you can see that, like, with OR, what's going on is it just takes all the ones, regardless as to where they occur, right? So that's how that sets one bit to high without touching the rest, without affecting the rest. If you wanted to, like, for example, turn a bit off, you would... Oh my gosh, I got a lot of questions. If you wanted to turn, like, say, bit 8 off, you could do something like this. This might not be the best way of doing it, but... yeah. So, bitwise AND with every bit except that bit. That would result in, of course, 0 for the bit that you excluded, and one, and, you know, it would just copy the rest for all the rest of the bits. Right? Oh my gosh. So many questions. Is the address supposed to be in hexadecimal or binary? Oh, shoot. Ha ha. Yeah, it's in binary, sorry. My bad, guys. Whoops. I'm sorry. Man, people are just blowing up my phone right now. It's crazy. I hope nobody's, Jeez. Yeah. So how does the microcontroller read values from a sensor like an ultrasonic sensor? If it's either a 1 or a 0, then how does it know the difference between a distance of 1 meter and 5? Well, basically, there's a difference between serial and parallel communication, right? So if you, like, those are the two main ways of transmitting a number, right? So generally speaking, if you're communicating via a parallel interface, then say you use 8 pins, right? And you just drive those pins to represent a binary number, you know, like, you know, binary number, right? And they can all transmit at the same time, and it's very fast, but of course it uses more pins. So if you're, like, most of the time, these types of peripherals will be using serial communication. In particular, I think a lot of ultrasonic sensors use I2C. I could be wrong. They could use UART as well, but we're going to be talking about the serial communication protocols in a later lecture. But essentially, by sending a series of 1s and 0s that have all been timed out, and you can construct a data packet, and you can send that data packet out over serial communication. But yeah. So ADC, analog to digital converters, return a maximum. Yep. So you can also communicate, as Ariel points out, you can also communicate like partial numbers via analog communication. Although, you know, analog is normally reserved for analog sensors and analog like transducers and like temperature sensors and that sort of thing. Like, if you're communicating to a peripheral device, converting that signal to an analog signal, then back into a digital signal, just, like, it introduces too many operations on the signal. You can lose a lot of the fidelity. So digital is very high fidelity communication. So generally, it's pretty reliable. Pretty sure assembly is hex, but I don't know. Machine code is certainly binary. Hexadecimal and binary are the same thing. They're just different ways of representing the same thing, which is bits. How are we toggling bit 3? Okay, I can do that one as an example as well. So, let's say we had this guy, right? Exclusive OR is 1 if the two inputs are different, and 0 if they're the same. So, if you have, so the result of this would be 11000001. So you can see it has flipped this guy from a 1 to a 0. And the interesting and cool thing about bitwise is if you do the same thing twice, you get the 11000101. So you can actually reconstruct the thing by, like, if you apply exclusive OR twice, it resets you back to your original condition. What's the difference between analog and digital signals? Yes, yeah, going back to 2E is like, yeah. You have to know how the sensor works, but I'm pretty sure ultrasonic sensors measure the time between when the wave is emitted and when it's received. Yep. I think that ultrasonic sensors aren't the best place to start, though, because distance is an analog value. I'm not really certain what you're asking about. Yeah, like we have a whole topic on analog to digital conversion, so I'm going to leave it off there. We can talk about that there, because we have some other interesting electrical things to talk about. So, so for the STM32L4, you've got 8 GPIO ports, A, B, C, D, E, F, and G, each up to 16 pins in each port. So that is way, way more pins than you would ever need for any purpose. Like, most of the labs, I think, will use a maximum of, like, 5? Possibly 4. No, like, possibly 8, but you shouldn't need, like, that many pins. Anyway, so, this is what a transistor is. I'm not sure why this slide is here. To remind you what a transistor it is, I suppose. You guys studied transistors, I'm sure. Transistors are the basic electrical component in digital systems. Acts as an on-off switch. Voltage at gate controls whether current flows from source to drain. Don't confuse this gate with a logic gate. So this is just like, you know, depending on whether it's, you know, depending on how you dope the silicon, this can either, like, allow the current through if this is high or low, but this is, like, this is the essential, you know, this is the discovery that was made that has enabled the modern world. Understand, transistor equals switch is about it. Oh, that's a shame, because that was supposed to be a physics course. So, I'm not prepared to talk about how the physics works, but I can tell you that, just from memory, when you make silicon, you can embed in that silicon either a positive or a negative charge by including in the silicon's crystal matrix positively or negatively charged ions. I believe they use boron and something else. So basically, by putting these groups of positively and negatively charged silicon together, you get interesting electrical characteristics. Like, you know, you've got PNP transistors. That PNP transistor is positive, like positive, negative, positive, and it refers to how the silicon has been doped. Arsenic. Thank you. Yeah. So, like, you don't have to know how it works, but it works. So, let's talk about GPIO input. So this is an important slide, right? Basically, when you consider the input coming into a microcontroller, it can have one of 3 states only, right? So it either has a high state, a low state, or a high impedance state, also called floating, tri-stated, or high Z, or Z. Yeah. Oh, there's this really cool game, like web game, where you have to design circuits with transistors and stuff. I forget what the game is. Anyway, so high means that you're receiving a high input. Whatever the settled state of that pin is, it's above whatever the threshold is to be considered a high voltage, right? Similarly with low, that low means that the pin is currently grounded, or it's, you know, it's at 0 volts, right? High impedance basically means that the pin is unconnected, right? it's either unconnected or connected to something with a sufficiently high impedance that no current can flow through it. High impedance state can also be caused by something like a turned off transistor. But, so like you can quote unquote disconnect it with a transistor. You don't have to actually physically remove the plug, although it's effectively the same thing as removing the plug because, air has a pretty high impedance. But, so essentially you've got two ways of configuring your input pins. Again, on the ARM architectures, you can just configure whether or not you use this pull up or pull down. But on like smaller systems, you may have to work with either pull up or pull down exclusively, depending on the microcontroller that you're using. So essentially, in high and low state, there's no difference between pull up and pull down, right? The only difference between these two is when the input pin is in a high impedance state. So if the input pin, let's take pull up resistor for a moment, right? If the input pin is in a high impedance state, that means no current can flow through this wire, right? Because we assume that no current is flowing through the actual input, right? This is kind of like how we assume that current doesn't flow into op amps, right? So if this is just floating, then there's no amperage here, right? Since there's no amperage passing across the resistor, there's no current drop. So if the external input is high impedance, then this is going to read high, right? It'll read high, irrespective of, any other factors. Pulled down resistors are in fact the opposite situation, as you might have guessed. You've got 0 volts down here. If there's no current going across the resistor, then that means that the input is at ground, which means that it reads low in high impedance states. Generally speaking, I think that probably, it depends on whether you need, it depends on whether up means whichever, if a high voltage state is more meaningful, then you want to use a pull down resistor, and if a low voltage is more meaningful, you want to use a pull up resistor, because then you're grouping high impedance state with the less meaningful outcome. So I've got quite a bit of chat log. I remember hearing some more complex analog computers. Oh yeah, they've been working on that since the 70s, man. They're starting to reach the point where transistors are near the atomic... Yes. Oh, I can explain that effect, actually, that Avery's talking about. So... basically, the problem that we now have with transistors is that there's only so small you can make them. In particular, the circuits, it's like when you have insulation between two wires, it turns out that electrons can actually spontaneously jump that gap if it's too small, even if it's insulating material. So this is an effect called electron tunneling, and that's one of the physical limits on how small a chip can get. But yeah, we're definitely we're in the phase now where transistors are the relevant metric is how many atoms they are across. Truly, it's some Star Trek level stuff that's going on with these chips. Yeah. Yeah. Yeah, and we're actually going to see why computers are limited, like it's all electrical limitations, right? What will the screen on our microcontroller be used? A lab. So we want high or low input with a pull-up resistor. So all this is really saying, if your input, like, presumably the input pin being disconnected or in a high impedance state, presumably you don't want to read that as a valid input, right? So it depends on what you think is valid. Like, there are push buttons that you can press which disconnect a line when you push the push button, and there are push buttons you can get which connect a line when you push the push button. So it depends on whether 1 or 0 is meaningful. If the 1 is the one that's meaningful, then you want to group high impedance with the non-meaningful input. Like take a push button switch, for instance, right? If the contact is closed, and that, like, if pushing it closes the contact, then that means you put 5 volts at one end and you read that 5 volts on the other hand, and when it's disconnected, that means it's in a high impedance state. If you're using a pull-up resistor, you won't be able to tell the difference between the button being pushed or not, right? Because in both cases, it's going to read as high. So, one of two things. You either have to use a pull-down resistor instead, in which case high impedance state will be read as low, which means that you'll be able to tell the difference between the button being pushed or not, or you connect the you leave it as a pull-up resistor, but you connect the other side of the switch to ground, so that a 0 volt, like a low signal, travels across the switch and into the controller. So when is one of these preferred over the other? It's really quite situational, but it'll be dictated by the hardware. Basically, one of these you'll get meaningful results, and the other you won't. It depends on how the circuit is hooked up. Intel says they're on pace to break Moore's Law. Yeah, we'll see. Let's see. If you could somehow activate GPIO with your body and think you are using force to click a button, your pin is probably floating. This has happened to me many times, and I always think I'm breaking physics. Yeah. Okay. If I'm not pressing a button on my keyboard, I don't want my system to be reading it as high pressed. A pull-down resistor would set the state to low so there's no floating. It doesn't matter which one we use so long as your input state is the opposite of the resistor. Exactly, yeah. If there is a signal, basically it overrides whatever the pull resistor is. Yeah. Yeah, this only really matters for, like, high impedance states, right? Like, if you send it low, it'll read low with either of these. If you send it high, it'll read high with either of these. What is important is when it's, like, disconnected, or when it's a high impedance, because there are actually, like, quite a lot of, like, use cases for that. Okay, what is an example of where a pull-up is necessary? Again, a pull-up is necessary if you have a switch, like a push button, that's connected to the voltage source, and then that's fed into your pin. That's got to be a pull-down resistor. So the idea of a pull-up resistor is like, it's a general thing that's used in electronics. Connor is noting that you can turn a 1 volt wave into a 5-volt wave. It's the same physical process, but you know, this is using it for a different purpose. Yeah. So you want high to read correctly without mistakes if we want a pull down resistor. Yeah, well, you know, it's high impedance isn't necessarily a mistake, but yeah, I'd say we're there. Oh shoot, it's already class is over 2 minutes ago. Okay, I guess next time we'll talk about GPIO output. We'll talk about how output pins are configured. Next time. Wow. Any questions? Yeah. Why can't you just make CPUs bigger to have more transistors on board? Yeah. Yeah, for one thing, yeah, as you increase the size, you also increase the price. But believe it or not, a very major factor with these things is that they need to not melt when you turn them on. It's all about heat dissipation, you know? Cool. All right. Awesome. Yeah, and if you haven't had, I think nobody's had a lab for this class yet, I think the labs start tomorrow. Am I right about that? Let's see here. Yes. Good luck on the labs tomorrow. Lab section 2. Take her easy, folks.